Hi, my name is Abhishek Jain. I am a student of Masters in Computer Science at Arizona State University. I'll be presenting this video for the course CSE598 Topics in Data Systems. Today we'll be learning about spatial query languages. A query language is a principal component in database management systems. Conventionally, SQL has been the lingua franca of the RDBMS world. The sequel is built upon a more formal language called relational algebra, which is not often directly used as a query language in database management systems. Since spatial database management systems are extension of relational database management systems, so it's natural that a query language for spatial database management systems will borrow some of its features from SQL. Let's study about the relational algebra. Sample operations for, let's say, two relations R and S in relational algebra will include union, which returns all tuples which are either in relation R or in S. The difference, R minus S, returns the tuples of R which are not in S. Intersection returns tuples which are in both R and S. Cross product returns a relation whose schema contains all attributes of R followed by all attributes of S, applicable to any pair of relations even which are not union compatible. Join can be thought of a cross product followed by a select operation. SQL, which is known as Standard Query Language, it was developed by IBM and it has become a standard query language for relational database management systems. The two major components of SQL are DDL, which is Data Definition Language. It is used to create, delete, modify the definition of tables. Second, the Data Modification Language or Data Manipulation Language. It is used to insert, update, delete, or select records from the tables. Now let's study about query language for spatial database management systems. OGIS standard. It is based on geometry data model consisting of base class geometry and the derived classes point, curve, surface, and geometry collection. OGIS operations fall into three categories. The first, basic functions, which include boundary, is simple, export, etc. Second, the topological or set operators, which include equal, disjoint, cross, within, contains, and overlap, etc. Thirdly, the spatial analysis, which include operations like distance buffer, convex hull, etc. The limitations for using the OGIS operations based on OGI standard are that these standards are limited to object model of space, that is too limited, that too they are limited to operations like select, project, and join. So they are not extensible for the field model of the space. Talking about the spatial storage and indexing. Indexes. Indexes are data structures which are used for faster and efficient retrieval of data from the databases. The storage in spatial database management systems. Unlike the relational database management systems where the cost of data transfer from secondary memory to primary memory is the efficiency measure, in case of spatial database management systems, following factors are to be considered. First, spatial functions complexity. Spatial functions are progressively more complex than the relational database functions. Secondly, the storage requirements to store the spatial data, which usually is disk intensive. We should note that the data that is to be captured by the spatial databases is usually in terms of the images or the other geographical data, which does not have the inherent representations or the data types available. So representing that spatial data in terms of the available or conventional data types can be more intensive on the disk. Now, traditional storage concepts which are extensible to the spatial data. The first one we'll study about the disk geometry. It is concerned with the three type of times like the seek time, the latency time, and the transfer time. Second component is buffer manager, which is actually a software module to handle task of data transfer between the secondary and main memory. The third concept is file structure, which include the unordered files or heap where there is no order for the storage of the files. Secondly, the hashed files, which is usually implemented using the hashing techniques and is a proven way for efficient point search, insert, and delete operations. Third structure is clustering, where the goal is to reduce seek and latency time. It is implemented using the Z ordering, Gray code, and Hilbert code. Spatial indexing. Index files are auxiliary files used to speed up the searching of data files. Records in an index file consist basically of the two fields. The first one, the key value. The second one is the address of the page in the data file. Ways of providing a spatial index. There are two ways. Firstly, the dedicated external spatial data structures, which is analogous to B-tree implementation. Second, the space filling curve, which maps the spatial objects to one-dimensional space using Z-order or the Hilbert curves. Other implementations. R-trees. R-trees are the k-dimensional height-balanced B-trees which are characterized by the leaf nodes containing a range of small m to capital M index records, where the capital M is usually the number by half the total number of records. Second, the bounding rectangle for each leaf node, which contains the k-dimensional data object represented by the indicated tuple. Thirdly, the known leaf node, which has the children ranging in the range of small m or capital M unless it is root. Now we study about the R plus trees. R plus trees are characterized by following properties. All leaves are at the same level. Second, the root has two children unless it is a leaf. Third, two intermediate nodes are non-overlapping. Fourth, for each entry in intermediate node, the subtree rooted at node pointed to by child pointed contains a rectangle R if and only if R is covered by that intermediate node. The only exception is when the intermediate node I is a rectangle at a leaf node. Now let's talk about the concurrency control measures. We know that conventional DBMS deals in terms of transactions which are characterized by acid properties, namely the atomicity, the consistency, the isolation, and durability. The concurrency is controlled by techniques like two-phase locking or the 2PL protocols, where a read action acquires a shared lock on the resource and a write action acquires an exclusive lock. The second property of this two-phase locking protocol is that all locks associated with the transaction are released when the transaction gets completed. In case of the spatial databases, following strategies are used to achieve concurrency control. In case of B trees, only one node should be allowed to get logged at a given time. Second, the B-link strategy, which works by adding a write link from the node to its sibling on the same level, searching on the levels of the split nodes. Third, the R-link tree uses a monotonically increasing logical sequence number to track the split nodes. Now we come towards the query processing and optimization. Query processing and optimization is divided into two steps. First, designing and fine-tuning the algorithms for each of the basic relational operators. Second, map high-level queries into a composition of these basic operators using information from the above step. Let's compare the query processing and optimization in terms of relational database management systems versus the spatial database management systems. Spatial database management systems do not have a fixed set of operators which is usually available in the relational database management systems. Secondly, the spatial extensions of objects in spatial databases cannot be sorted in one-dimensional array, unlike the relational databases. Thirdly, the spatial databases require progressively complex algorithms for processing spatial predicates, and the input-output costs become less significant as compared to the processing costs. Talking about the spatial operations, following spatial operations are available. The update operations, which include the standard database operations like create, modify, etc. The selection operations, which can be of the two types. First, the point query, which pertains to finding all the spatial objects containing a query point. For example, a query which says find all the points in a rectangle, or find a point contained by all the rectangles. Second, the range query, which pertains to finding all overlapping spatial objects. Sample query can be given a list of rectangles. A user may ask to find all the pairs of the overlapping rectangles. Third spatial operations is spatial join, which is analogous to relational databases joins, but with the spatial predicates like overlap, intersect, distance, adjacent, is enclosed by, etc. Fourth spatial operation is spatial aggregate, which pertains to finding the nearest neighbors. More specifically, like find all the spatial objects having a minimum distance from another spatial object. The processing of the object operations is a two-step process, which includes the first step of the filtering, where the spatial objects are represented by simple approximations, for example, minimum bounding rectangle. The second step is refinement step, which pertains to examination of exact geometry of each element and each spatial predicate. There are two types of spatial join algorithms. First one is the nested loop, where all the pairs of tuples of two relations are enumerated and tested for overlap. The time complexity for this nested loop algorithm is big O of n square. Indexing on one of the relations can reduce the complexity to big O of n. Second type of algorithm we have for this is tree matching, which works on the fact that each node entry contains information about the pointer to its children and the minimum bounding rectangle for the entries of a child node. The spatial aggregate operations, which usually consist of the two passes. The first one, minimum distance calculation, and the nearest neighbor search. In case of the R-trace, algorithms like breadth first search or depth first search are employed for efficient search over the adjacent nodes in the same level or the successive levels. Talking about the query optimization in spatial databases. Query optimization in databases is handled by a software module called Query Optimizer, whose procedures can be divided in two parts. First, the logical transformation, which again is a two-step. The first step is parsing, which includes generating the query trees. Second, generating the equivalent query trees based on the spatial operation heuristics. The second part is dynamic programming, which is used to select the optimal execution strategy from a set of execution plans based on some cost function, which can consider the following factors. The first one, access cost, which is the cost for searching and transferring data from secondary storage. Second, the storage cost, cost of storing intermediate relations generated during query execution. Third, the computation cost, the CPU cost for performing in-memory computations, and the communication cost, the cost for transferring information between client and server. With all this information, we are done for today. Thank you.